Okay, folks, last lectures for diodes. So we finally, after the next test, get to move on to transistors. And so the photo of the lecture here to kind of get our thinking started is shown here. And one of the things I'm going to ask you is, what is this, essentially? What are we looking at? And what kind of device might we be testing here? Well, you're used to basically working with devices when you're doing electronics design or digital design that are packaged in a nice package, right? So they come in a nice black package with 14 pins. You can easily put on a breadboard, or maybe you can solder it onto a printed circuit board. But the point is, when you're doing semiconductor work, you don't have these nice packaged chips when you're doing the development of the chips. And so you typically fabricate everything on top of a semiconductor wafer, which you can see here. And if you look, you can see little dies, which are each chipset shown here. And when you want to test these things, you basically bring down these tiny little probes down onto the surface of this. And you're doing all this under a microscope. So you're looking down at this through a microscope. And then you move this back and forth very finely to go from test die to test die to see how your device has worked out. And so, again, when you work in semiconductor device design, the testing is actually done on the wafer itself, and then later you go finish the packaging. A reminder, the test is next, okay? Make sure you look over the old example test problems that I've posted before you come to class. I'll spend most of the time answering any questions you have on these. So this is basically a review session for you this week as well, so make the most of it. Okay, so we're going to talk about breakdown today, and just so we start off with some review to make sure we're solid on our diodes. At thermal equilibrium, we've got no voltage applied to a diode, the Fermi levels line up, and all our drift and diffusion currents cancel out, so there's no net current. If we put forward bias, it's the same as putting plus on this side, minus on this side, and plus takes the bands down, minus up, and so then we have a ton of electrons here that can start to diffuse this way, a ton of holes which can diffuse this way because we've lowered the barrier for them to diffuse. We still have drift current, but it's small. When we go to reverse bias, the high concentration of electrons are trapped way below this large barrier. High concentrations of holes trapped way below this barrier, so they can no longer diffuse over. And so our diffusion current goes to zero, and all we're left with is thermal generations of electrons near the depletion region that move around and then can fall off to the other side. And thermal generation of holes, and electrons creates a hole. It can move around if it's close enough to the depletion edge. It will also be swept across. Now, when we've looked at these diode plots, in this course we've assumed that here's forward bias, and as we go to reverse bias, it stays constant in current indefinitely. But what we know, based on practice, and many of you have created this puff of smoke in electronics lab, is that you get to a certain voltage on reverse bias for a diode, and it will break down. And so notice this sudden increase at a large reverse bias. Basically, you've got your contact potential minus the breakdown voltage. So you're basically, your breakdown voltage, how much voltage are you applying above the breakdown voltage? And so if the breakdown voltage was 4 volts and you're applying 6 volts, you'd have 6 volts divided by the resistance of your circuit. And I put a resistor here, but you don't have to have a resistor in the circuit. The semiconductor materials themselves have resistance. And so this resistor could just be representing the inherent resistance of the semiconductor materials themselves. The point is, on this plot, once you get to breakdown, you get a very large increase in current. Now there's two ways this can happen, and they're both important. One approach is designed for low voltage breakdown, which is stable, meaning that I could have breakdown and then I could reduce the voltage and come right back here. And so this is reversible. And this is done by Zener Breakdown, which is related to tunneling. The type that is the puff of smoke type is at higher voltages typically, and that's Avalanche Breakdown. Think lightning bolts, okay? And that's far more destructive. So let's look at both types of breakdown today. So let's first talk about Zener Breakdown. And so, the question is, who remembers what tunneling is? Well, we've talked about this a little bit recently, but tunneling was basically, predicting my chances of walking through a wall. And it turns out that there's a finite chance that I could walk through a wall perfectly to the other side without any hurt to myself or damage to the wall. The problem is the probability is really low. So just like me, you have an electron here, and let's say this is the wall. It's a really thick barrier. It's got an energy mu naught, and it's got a width d. And so just like an electron, my probability of getting from here to the other side of the barrier is low, and so I'm just basically rejected from this. So I come up to it and I just bounce right off of it. And this barrier here, it could be a couple things. It could be vacuum. So if I have a metal here and a metal here and this is vacuum in between, that would be a barrier. It could be that this is my conduction band here, and this is a narrow band gap semiconductor, then a wide band gap semiconductor, narrow band gap semiconductor. Or it could be that this is a semiconductor, this is the dielectric, and this is a semiconductor. Or in the case of this lecture, we've got a semiconductor, this is the depletion region, and this is a semiconductor here. All of those create a barrier. Now, what we'll find out, which is interesting, is that if we make this barrier thin enough, if we reduce the width, then an electron can tunnel through quantum mechanically. Remember when we did quantum mechanics, you could, if you had a potential well, and you looked at some of the wave functions for an electron, kind of look like this, right? And so this was just basically giving you, the wave function just gives you the probability of finding the electron. If you take the square of the wave function, that gives you the probability of finding the electron. And so in this case, the electron's not going to go here or here because it's just going to be rejected. But with tunneling, let me get the eraser out here. If I basically were instead to have a barrier that's very thin instead, you'll find that there's a finite probability, according to the wave function, that the electron could show up here on the other side of this barrier, okay? And so quantum mechanically it's able to tunnel through to the other side. Well, we have the same thing here. We have a barrier, but we've made it so thin that the wave function for this electron will partially penetrate to the other side, giving it a probability to exist on the other side, and so therefore it's able to jump the barrier and appear on the other side. Now, how do we predict how much tunneling we get? Well, the percent of electrons that are able to tunnel will be proportional to the exponential of the tunneling coefficient A and the thickness of the barrier. And so, obviously, if A or D are large and this is negative, then my percentage will be very low, right? So if D becomes smaller, then eventually, if D goes to 0, then this could go to 1, right? And so I want I want small d and a small a to basically give me a large percent of tunneling. And again, d is the width of the barrier. The tunneling coefficient can be predicted as follows. You've got 2, the effective mass, the energy of the barrier, and so a larger barrier height will increase A, which will reduce my percent tunneling, so I like barriers which have less energy. I've got the energy of the electron itself, so if the electron has more energy, its chances for tunneling increases. And the last thing is we divide by h bar, which is Planck's constant divided by 2 pi. I won't expect you to do these calculations, but I just want you to see that the most important thing is that your percentage of tunneling, your chances to tunnel through, increases exponentially as your width d decreases. So, in this course, for a p-n junction, we can actually change d in the case of a depleted region dynamically. So let's take a look at that. So, how could we change d? And in the case of a p-n junction, the barrier for tunneling is right here. It's this band gap between the valence band and the conduction band. And so you could imagine that if I have, a carrier here or here, one way to get from this side would be to have the carrier go in this direction or in this direction through the bands. We've always assumed they go like this. They go over top the conduction bands and along the valence band as well. But through this barrier, what if they could go straight from here to here or from here to here? If I do that, I could get a different type of current which would be proportional to the percentage of tunneling. It would be a tunneling current through that barrier. So how can I basically make d small? Because if I make d small, the barrier width decreases and I've got a higher percentage of carriers which can get back and forth through this thing. Well, one way to do that would be to increase our reverse bias. So if I basically put more reverse bias on this, put this down, I get more slope here, maybe I reduce D a little bit, but one of the problems is remember, when you increase your reverse bias, your depletion width also increases. Now I know I didn't draw it really well here because this W looks the same as this W, but remember, when you increase your reverse bias, your depletion width also increases. So maybe these become higher sloped, then I decrease D a little bit, but the net effect is not that strong because my depletion region width is also increasing when I reverse bias a diode. What I can do that will be very effective to reduce D down is to increase the doping level. So here I've reverse biased it, but I've also made this heavily p-type doped and heavily n-type doped. And when you do that, that decreases your depletion region width, right? Because you don't have to go as far to uncover the amount of charge you need to get your contact potential. And so this will allow me to start seeing tunneling take place. And so let's see how this could happen. So I put a large reverse bias on this, okay, which means I put positive here and negative here. So if I put reverse bias on this, it's the same as putting positive voltage on this side and negative voltage on this side, okay? So in terms of current direction, obviously based on the electric field here, I want electrons to go this way and holes to go this way based on the voltage that's applied, right? Well, what can happen is, remember, the valence band is just a bunch of silicon atoms, right? And so anytime we get an electron left the valence band up to the conduction band and left behind a positively charged hole. Well, if that process can occur across this barrier in this direction, if we make D small enough, I can have an electron leave a silicon atom in the valence band and get to the conduction band over here, which is an easier route than going this way. And so my electron leaves a silicon atom in the valence band, moves over here, and again, we call it valence band because that's where the valence electrons of the silicon are that are available for this. When this happens, the electron made it over here. If I take an electron away from a silicon atom, that creates the hole, which is the absence of an electron. So what I've done here, through tunneling, is created an electron and a hole, and those can continue to propagate if this is negatively charged. The plus can keep going this way, the minus can keep going this way, and I can start to see current flow as more electrons jump this way, they travel this way, and the generated holes as a result go this way as well. So it's basically like electron hole generation, but now it's sideways this way instead of vertical, okay? This type of breakdown is referred to as Zener Breakdown because it's stable typically. It's based on tunneling, and so you can get the current to flow and it doesn't have to basically cause a puff of smoke to occur. The device can operate stably this way. Now, if we don't design for Zener with heavy doping on either side, another type of breakdown can occur, which is due to ionization. So look at this band diagram here. What do we do to this semiconductor? Just look at it real quick. Well, you know that as soon as I have slope bands, that means I've got electric field, right? And so I have a voltage dropped over distance, which is electric field. I know that electrons will go this way. But if you think about it, why should an electron go right down along this slope, right? Because as it goes from here to here, it's giving up energy, right? What if it wants to move over here, but not give up its energy? Because this is an energy band diagram, energy versus distance. And so look what happens. An electron goes over here, and let's say it made it to here, and its energy is greater than the band gap energy. Well, if it has energy greater than the band gap energy, the electron can come down to the conduction band, give up that energy to the silicon atoms, and as that electron came down and gave up its energy, it created an electron-hole pair. That means the electron came down, gave up its energy to the silicon, causing thermal generation, or in this case, direct thermal generation, or energy generation, of an electron which is kicked up from the valence band to the conduction band, which also creates a hole. So now you can see this multiplication where one electron got enough energy to create two electrons and a hole. Now, this hole could move over here, right? And now it has a lot more energy than the band gap energy, so the hole could come over here, relax back to the conduction band edge, give up all that energy, and lo and behold, create two holes and an electron. Basically, the original hole comes over, gives up its energy. That creates another electron hole pair as an electron goes up here, and now I've got more carriers as well. And so what you can see here is that this multiplication could continue and start to become substantial, potentially run away at some point. So how can we calculate this? Well, let's assume we have a probability for ionization, okay? And so the probability is not 1. So obviously, if the probability is 1, this would happen every time. So it's somewhere between 0 and 1. It won't happen all the time, but it won't happen none either. And the competing processes are things like scattering. If I have an electron trying to make it here, it could run into another electron and give up its energy. An electron trying to go here is trying to get a lot of energy. It could also run into some silicon atoms. So when it's moving here, it could bump into a silicon atom and instead basically give up its energy. So the probability is not 1 that it can make it here without bumping into anything else and giving up some of its energy. Because to get here, it can't give up its energy, right? It needs to basically move here, keep its original energy, then come down. So assume there's a probability for that. And the probability doesn't have to be equal for electrons and holes. One can dominate, but we'll keep it. And so we have this process where an electron goes here, and let's say it runs into a silicon atom. It gives up its energy to the silicon atom. Say the electron tries to get going, and it runs into another electron, gives up its energy. Finally, it goes far enough that it has enough energy greater than the band gap energy, and then it causes impact ionization of a second electron-hole pair. Okay? This process is referred to as avalanche breakdown. Start with one little snowball, and you end up with a bunch of carriers at the bottom. You can see the analogy here and where we come with the idea for avalanche. So again, let's assume we have this competing process of trying to lose energy, but also trying to gain enough energy to cause impact ionization. And let's assume our probability is between 0 and 1 for electrons coming in to cause impact ionization. And let's assume holes have the same chance as well. Okay? So, let's let this play out here. Here's my depletion region with W. Here's my first electron coming in. Let's say this thing has no carriers, and my first electron comes in, and it goes all the way here, and it finally gets enough energy to generate a second electron hole pair, so a hole starts going this way, and then I get 2 electrons going out to the other side. And so my probability of that happening would be the number of electrons coming in, okay? So my current I have first will be the number of electrons coming in, but in this case, the total current will be the number of electrons coming in plus the probability of generating more electrons, which is probability times the number of electrons coming in. So if I have 5 coming in, here's my 5 coming in, and for those 5, they have a 50% chance of generating another electron hole pair, then I'll have my 5 coming in plus 50%, 0.5, times that same 5 coming in that are generated as well. So it increases. Then I go to this hole here. Let's say, look at this hole. Well, this hole moves along, and it could have a probability also to generate an electron hole pair, right? And so the number of holes I have was basically the original number of electrons I had coming in, N, times the probability that the hole was created. I move that here, and then I multiply it by the same probability again, which means for those that were created, what's their probability to cause this to happen a second time? And it could keep going further. I generate an electron hole pair, right? And it goes this way, and so then I have basically, I had N, my first event, which then can lead into my second event, which could lead into my third event, and you keep multiplying by probability out. You'll notice here that we're basically developing a power series approximation. Okay? So, one thing some of you that are smart might notice is that, well, look at this. If I have a hole, you know, electron had all this distance to get the energy it needed, right? Well, you know, this hole doesn't have as much distance to go to gain the energy it needs, right? And so it only has this much distance, whereas this electron could have used the whole width to get the energy it needs to cause a generation of a second set of electron hole pairs. You don't have to worry about that, though, mathematically, because look at this. If the electron had this whole width to try to do what it needs to do, when you look at these systems, sure, a hole only has this width, but the electron that was generated has this width too. So if you look at the path for the electron plus the path for the hole, both of them combined give you the total width. So your probability can be assumed that together the hole that's generated and the electron that's generated together have the whole width W to generate more carriers. Okay. So they typically don't have to go as far before they generate something. But again, let's look at this power series. And so we end up with this, which again is a simple power series, which we can equate using this simple approximation, not approximation, this equivalency here, where here's my probability, here's my number of electrons in, and my multiplication factor for this type of a device, which will be the number of electrons coming in over the number of electrons coming out, is basically equal to 1 over 1 minus the probability. Okay? And so that means if I have a diode that's reverse biased to the level of avalanche, I will get multiplication. And if the multiplication's strong enough, this NN will basically lead this to run away at some point and cause a puff of smoke. It could also be controlled such that I'm just at the point of avalanche where I bring in 5 electrons and the multiplication factor is 1,000 and I get basically, 5,000 out. Okay? And so you can have a diode where just a couple of electrons that start to make it across the depletion region lead to a ton more, and you can see your reverse saturation current increase substantially. If you look at a diode spec sheet, you'll typically see it expressed like this, where it's 1 over 1 minus the applied voltage divided by the breakdown voltage times this ideality factor, which is between 3 and 6. Okay? Here's a nice multiplication plot that you can do in MATLAB. So they're plotting it versus the breakdown voltage, and they're plotting it for a couple. I think this is actually for the n value, n equals 6 and n equals 3 here. One of the things I want to emphasize is that just because you have avalanche does not mean it can't be controlled. So again, you can bias this such that you're all set up for avalanche, but that it won't run away and turn into a puff of smoke. And so one type of device which is utilized, which is quite powerful with avalanche, is an avalanche photodiode shown here. With an avalanche photodiode, what they do essentially is they bias the diode in reverse bias close to the point of avalanche breakdown. Okay? So you're learning a little bit about optoelectronics here. Okay? And so they'll bias this thing with a lot of reverse bias. Let's draw our diode here. Okay? And the reverse saturation current is pretty small, and so there's very little current coming through these leads. What happens is a photon of light comes in, it gets absorbed, and if the energy of the photon of light is greater than the band gap energy, I can create an electron-hole pair. An electron goes up here, a hole goes here. And now, because of the avalanche process, I will get out a ton of electrons and a ton of holes. And so one photon with a conventional photodetector would just give me one electron and one hole. But if we're biased to the point of avalanche, that one photon, because of the multiplication factor, gives me tons of electrons and tons of holes out. So I've got basically a photodetector with a built-in amplifier inside of it. And so, what is the value of that? Well, if you're doing a circuit, you could have basically a really, if I have a circuit here, and here's my photodiode detector, so here's my photodiode, and in a typical experiment I've got this long line here, right, which has got a lot of parasitic capacitance on it, right, and the line has some resistance. And so one of the advantages of putting the amplifier inside the diode is that if I have a long line or if I have parasitic capacitance that goes later to my amplifier, shown here, so here's my amp basically. Instead of trying to get the signal down this long line where I have RC time constant issues, if I amplify locally, I will be able to charge this line much more strongly and get the signal out of my circuit. So avalanche photodiodes will help to detect really weak signals, or it'll give you a higher frequency operation than you could achieve with a regular photodiode, given all the parasitic resistance and capacitance. Again, as we said, the breakdown is heavily dependent on doping levels. Okay, so let's say I have a P plus N diode, which we almost always have in this course, right? We almost always have one side doped heavily and one side doped lightly, and we'll talk about that in a second. Okay. Well, in this case, I've got a really long depletion region. Okay. And so this is a great long depletion region for the electron to get enough energy to cause avalanche breakdown. So this is a good setup for for Avalanche Breakdown. Now, if I dope this heavily, okay, then at that point, that reduces my depletion region width, right? The depletion region width decreases. My slope is increased here, right? But more importantly, my depletion region width right here has decreased, and I can start to get tunneling current through here. So at some point, I increase doping. I'll see a lower breakdown voltage because my slopes get steeper here, easier to get enough energy for avalanche. And so, increased doping, I get lower avalanche breakdown voltages, right? Because the slopes get steeper. And at some point, the breakdown will be taken over by Zener Breakdown, which is tunneling. Let's take a look at that the next slide, and we'll see if it works. So here is a plot of breakdown voltage versus doping level. Again, you can see for all these different semiconductor systems, okay, and this is assuming a P plus N diode, assuming P plus N, so they're just plotting the N-type concentration here. You have silicon, germanium, gallium arsenide, gallium phosphide diodes. You can see for all of them, like silicon, as you increase your doping level, your breakdown voltage decreases. So this is all avalanche breakdown, these curves here. So I basically increase my doping level, that brings in my depletion region, I get a steeper slope, so my electron doesn't have to go as far to have enough energy to relax and basically create a second electron hole pair, and so on and so on. So increased doping reduces my avalanche breakdown. At some point, you'll see, you get to the point where tunneling begins and Zener dominates, where you have enough doping on either side that D gets so small that electrons go straight through the depletion region in this direction. And so for all of these curves, this is the point at which you get Zener breakdown, and these are all avalanche breakdowns. So we've answered some of these questions. Look at the effect of doping. Why the lower avalanche voltage? Again, you have lower avalanche voltage as you increase doping, because as you bring in increased doping, decreased depletion region width, steeper slopes, easier to get avalanche, right? Look at the effect of band gap. Why do if I go from here to here to here, I get lower breakdown voltages? Well, that's simple, okay? If I have to basically generate an electron hole pair, then the amount of energy I need is going to be the band gap energy, right? And so gallium phosphide is wide band gap. Germanium is even narrower band gap than silicon. And so as I go to band gaps with less and less energy, like a narrow band gap germanium, it doesn't take much energy to create an electron hole pair. So of course, the breakdown voltage would be decreased. Now, look at the effect of band gap for tunneling as well. It's the same thing here. If I look at going from wide band gap to lower band gap, I see tunneling take over at lower doping levels than I would for wide band gap. So it basically you have to go to higher doping levels for wide band gap to see tunneling occur compared to lower doping. And that's just because if my band gap is reduced, then D already has a starting point to be thinner and get to the point where you start to get tunneling. So let's look at some applications, some really simple applications. Obviously, when we want rectification, we do not want Zener breakdown. And so if you want a diode that does not break down, you do not want to dope it heavily, okay? And so here's a half-wave rectifier, and here's a full-wave rectifier. These are pretty simple circuits, right? So if I have this basically, if I'm flowing current in this direction, it goes through the load this way, right? And yeah, it goes through the load this way, and that gives me current through the load. And if I have current in the other direction, it finds the same path, but it goes this way instead. And so I get rectification for both the positive and negative phases of the AC cycle. Sometimes you have very high voltages for rectification. These are used in commercial LCD and plasma TVs and automotive applications. These are 250 volt Schottky rectifiers, meaning that they'll rectify up to 250 volts before they break down. And typically these higher voltage rectifiers use wider band gap materials like silicon carbide and gallium nitride. Again, wider band gap, harder to have ionization of an electron hole pair. So these basically increase your breakdown voltage. But again, remember these materials, it's hard to do p-type doping, and that's why these things are Schottky diodes often. Here's some commercial spec sheets for some Zener voltages. And so if you look at this, they give the Zener breakdown voltage and the current. And so you can see when you're at low voltages for Zener breakdown, heavily doped, you can have a lot of current through it. And then as you go to higher voltages, the current decreases. I'm not sure exactly if these are indeed all Zener, or if some of these become Avalanche at some point at higher voltages. But I do understand the fact that if your breakdown voltage increases, then the maximum current it can flow should go down, because current times voltage is power dissipation, and these things can only dissipate so much power. So if you look at your power dissipation, that kind of has to stay a little bit consistent, because this thing essentially will turn into a puff of smoke. And so you can get a higher breakdown voltage, but then the Zener current, when it breaks down, has to decrease, otherwise it will turn to a puff of smoke. One last fun topic was related to my PhD work. You can apply Zener breakdown in a way that you can use to make displays. And so in my PhD work, and you won't be quizzed on this, but we basically built a structure. We had a light-emitting phosphor, which is a semiconductor that emits light when it breaks down. I have a really strong dielectric here, a really strong dielectric here, and then I've got a metal and a metal. The metal here is a standard metal like aluminum, and the metal up top is a transparent metal like indium tin oxide. We'll talk more about that when we do optoelectronics, but basically it's conducting and transparent. If you look at the equivalent circuit for this metal and this dielectric here acts like a capacitor, this metal and this dielectric acts like a capacitor, and this phosphor here in the middle acts like back-to-back Zener diodes with a little bit of capacitance. So if I'm below the breakdown voltage, there's no breakdown, and I just see this capacitor here in series with the other two capacitors. But if I go above a certain voltage, these will start to break down, and I will get current flow in between these two capacitors. The reason why I have these two capacitors is so this current flow doesn't run away. If I put a high voltage here, I'd like to break these down, but then have the current be limited by these capacitors. And so when you look at a band diagram, here's a metal, here's the dielectric, here's the phosphor semiconductor, here's the other dielectric. You put a lot of negative voltage here, a lot of positive voltage here, you get a ton of band bending, and all of a sudden you'll see electrons being ripped out from the interface. They get enough energy here such that they can excite atoms in the semiconductor, such as manganese, which then emit light. And so instead of having electrons which go and create other electrons, the electrons here get enough energy that they excite manganese atoms in the phosphor and cause it to give off a light emission. So I basically, in this case, I put negative here, positive here. The next thing I'll do is I'll drive this with AC, and then I'll put negative on this side, positive on this side, and I'll just switch it around such that the bands go this way, and I'll have the electrons go back this way, and then I'll switch it again. I'll have the electrons go this way, and I'll keep basically going back and forth between plus and minus, minus and plus, swishing the electrons back and forth at high energies, and then kicking out photons of light. Build this device up. This is what it looks like. The device has basically you have a bunch of row and column electrodes, and at the intersections you get pixels. Here's a zoom in of a display. We had a company called Extreme Photonics at the time, and here's zoom ins of the pixels. You can see them lighting up here, and this was a technology we were developing before LCDs became really popular at large scale. We thought this was a better way to make a really thin LCD, as you can see here, and also scale it to larger sizes, because back then they were saying LCDs could not be manufactured at greater than 20 inches. This is like 2001. And what we found out, of course, is that this technology wasn't going to compete with LCDs because they figured out how to make LCDs at greater than 21-inch diagonal. Another challenge we faced was that we could do great with yellow and green, but we had a really hard time creating blue. And if you want to make a full color TV, you need red, green, and blue together. Well, to do that, essentially, requires a lot of energy, right? And so the problem we had is that in these phosphors, we could get enough energy to basically generate red and green photons, and red and green and yellow are on the same energy spectrum. But blue, which has the shortest wavelength and the highest energy, you could not get enough energy in the electrons without them running into the other atoms in the semiconductor to basically get blue emission. It would blow up before you could do that. And so that was ultimately another limitation we had, in that you really couldn't make a full color display out of this. Okay, that is it. Make sure you can answer these questions before you go on to the quiz and before you go on to the final and last part of this lecture and the final lecture part for diodes.